In this video series, we're going to take a look at inverse functions. And what is an inverse function? Well, that's what we're going to start by defining. So an inverse function, we're going to define it. And then also we're going to take a look at the algebraic and geometric properties of what an inverse is. We're going to learn about the horizontal line test. And we're going to determine if we can use the horizontal line test to determine if an inverse exists. And finally, we're going to find an inverse function and verify the solution by showing that f minus 1 composed of f of x is equal to f composed of f minus 1, which both should be equal to x. All right, so here's a basic overview as to what inverse functions are. Consider these two functions, x plus 2 and x minus 2 for f and g respectively. And I think most people know that to undo adding 2, you would subtract 2, right? So if you gave somebody $2 to undo that operation, you would take back $2. And I want you to take a look at the table of values for both of those. So let's say, for instance, I were to substitute 1, 2, 3, 4 back into x for f. Well, I would just add 2 to each of these, and this would be our output, 3, 4, 5, 6. What if I were to take these outputs and stick those outputs back in to G? Well, what that should do is that should undo those, and that should get back to the beginning, which it does, 1, 2, 3, 4. All right. And so that's what we're saying is that an inverse function essentially just interchanges all the x for y and then also the y for x. And we remember that x is the domain, y is the range. And so what this suggests is that the domain and the range are going to be reversed, okay, for inverse functions. All right, so that's the big takeaway from this, is that the domain becomes the range and the range becomes the domain for inverse functions. All right, and that is going to be true for all inverse functions in their domains. So what we're saying is that all ordered pairs x, y that appear in the original function f, those are going to be yx on the inverse function. All right, so we have this f minus 1 of x. Now, f minus 1 of x is not the reciprocal. Okay, so not the reciprocal. All right, so be careful of that. Okay, sometimes students take a look at that and they think, okay, it's just going to flip over the fraction or flip over the equation or something of that nature, but it is not. All right, so to show that two functions are inverses algebraically. Now remember, inverse functions undo operations. And so what we would say is that if we compose the original function of the inverse or compose the inverse of the original function, that should get us back to whatever value we started with. Okay, so notice if we substituted x minus 2 back in for x plus 2, the negative 2 and the positive 2 would cancel and we get back to x. And that's exactly what we're going to see a little bit later in these video series. Functions that are inverses are reflections in the line y equals x. All right, we'll see that in a moment. And then we call a function one-to-one if for exactly each value in the domain, there's one value in the range. Okay. Now, to determine if a function is one-to-one, it has to pass this thing called a horizontal line test. And horizontal line tests can help you to determine if functions are one-to-one. All right. If a function passes the horizontal line test, it's one-to-one, which means that there's going to be exactly one output for every input, which means when we find the inverse and we flip those around, that means there's going to be one output for every input and one input for every output. All right, so that's why we need to do this horizontal line test before we find the domain, or excuse me, find if a function, to find an inverse function. Consider these two functions. F at x equals x cubed plus 1, and g at x equals the cube root of x minus 1. Those functions I think most people could see are inverses. A cube and a cube root are inverses, and then adding 1 and subtracting 1 are inverses. And I want you to notice that on the graph, this is the line y equals x, and notice that all the points on this function g, so this is our function g, and this is our function f in red, those are reflected in the line. So take a look right here. All the points, these points are equidistant from the line y equal x. All right, so we have this point and we have this point. and they're both equidistant. And I know I didn't draw those too well, but just think they're reflected in that line. For a function to have an inverse, again, it has to pass the horizontal line test. And so let's take a look at this function, x to the fourth minus x squared minus x. And I want you to notice that it intersects at least one time at two places with a horizontal line. Okay, but that's not the only one. Okay, there's one there, this one here. All right, there's a whole bunch of them. In fact, if I drew one here, it would intersect a lot of times. And I know that's not a good horizontal line, but again, difficult to draw on a computer here. So that might be a little bit better. Nope, that's even worse. But anyhow, you all get the idea that if it does intersect when you draw a horizontal line more than once, it means there's no inverse. Basically, in the first two exercises, we're just going to do this. We're just going to show that geometrically, and it's not going to prove it, but it's at least going to support that the following two functions are inverses, at least geometrically. Okay, so we have this x over 4 and 4x. All right, so let's go ahead and type y equals x over 4, and we have y equals 4x. And let's also plot the line y equals x. Okay, so on a graphing calculator, this is what you would do. Okay, I'm going to move this around a little bit. And I want you guys to take a look at a few points, right? So I think everybody can see that this point right here might be like 2 comma 1/2. So I'm going to say 2 comma 0.5. I'm going to label it. That means that on the inverse function, there should be a point 0.5 comma 2, which there is. Right? If I take a look a little further, this is the 0.41. All right, so let's take a look at the 0.4 comma 1. And there should be a corresponding point on the inverse 1 comma 4. All right, so pretty cool that those points exist exactly on those functions. And there's an infinitesimal number of points that are reflected in this line, even down here. Okay, so if I looked at the point -1, -4, then there should be another point -4, -1 on the inverse. All right, which there is. I'm not sure what happened there, so we're going to label it. So again, notice that these points exist. All right, so pretty cool that that's how we can geometrically at least support that they're inverses. Okay, now that doesn't prove that they're inverses. All it would take is finding one pair of points if they existed to show that they're not inverse. But we can't do that, okay, because these actually are inverses of one another. Right? Another example of this, we have 1 minus x cubed, cube root of 1 minus x. So let's graph those. Right, so let me get rid of all these points. We don't need those. So we have 1 minus x cubed, and we have the cube root of 1 minus x. Now, what I'm going to do is, instead of cube root, I'm going to type this as 1 minus x to the 1/3. All right. And I think everybody can see that a point that would exist on here would be 2, -1. All right, so I had 2, comma, -1. Right, and I'm going to go ahead and label that. And so what that means is that the point -1, comma 2 should exist somewhere on the inverse, all right, which it does. All right, so notice that these points exist. Right? Another point that might exist somewhere is if I had, let's say I plugged 9 back in, okay, that would give me, let's see, that would give us the point 9 comma -2, I believe. So if I had the point 9 comma -2, all right, that exists all the way over here. So that means the point -2, 9 should exist on the inverse. And I would label that, and I can't see it because maybe I'm just not zooming. Oh, there it is. Okay. So yeah, it's right here. Okay. So again, these points are equidistant from this line y equals x. All right. So again, this doesn't prove that they're inverses, but it does verify. Okay. So one thing that you should always do is when you get your answer, just graph it just to make sure that it does follow those examples. And maybe just pick a point that you know is going to fall on one function, and then see if you flipped around the range and the domain, if they would fall in the other function. Okay. All right, so that's just an introduction to our inverse functions. So in the next videos, what we're going to do is we're going to be able to verify inverse functions, but also we're going to be able to find inverse functions given one function eventually.